Today we are going to discuss relative velocity problems. In that, so you have problem of diminishing size. So these type of questions and the problems we'll discuss in today's discussion. This another type of problem on relative velocity. Here, three particles A, B, C are located at the vertices of an equilateral triangle of side D at t equals to 0. Each moves with constant speed v towards one another in cyclic order, such that A is always directed towards B, B directed towards C, and C towards A. After how much time will they meet each other? Basically, this problem, if you consider, this is a problem where it is called as the problem of diminishing size. In fact, if you can look at the diagram, you have an equilateral triangle. This is your ABC. Particles are located at the vertices of this triangle, and the side of this triangle is T. Here, A is always moving towards B. B is moving towards C, and C is moving towards A. They all move with the same speed v. And it is asked after how much time they will meet at a point. So, if you just casually look at the problem, in that case, you may not realize that how they can meet. It will just appear if A is following B, B is following C, and C is following A, then they will never be able to meet. They will just be following the sides of the triangle there. But it is not like that. In the question, it is said that A is always directed towards B, B towards C, and C towards A. Does not mean they are moving along this line. A in this direction, B in this, or C in this. In fact, if you consider that after some time, what will be the position of B? B will be somewhere here. So A will be basically directed along this direction. Similarly, new position of C will be somewhere in this direction. So B will be moving in this direction there, so that it is always directed towards C. Similarly, C will be directed to the new position of A all the time. So what you'll notice, after some time, particle A will be basically at this point, A dash. B will be somewhere here, and C will be at this point. Again, when A dash has to move, in that case, it will move in this direction now. Then B dash will move in this direction. C dash will move in this direction. So new position will be now A double dash, B double dash, C double dash. And now you look at the figure, you'll find that they are still at the corners of an equilateral triangle. Of course, its side will be less. It will go on decreasing. So that is why it is also called as the figure of diminishing size. And if you consider the path followed by A will be moving like this, B will be basically moving and following the path like this, and C will follow the path, so that they all will meet at this point. You have to basically find after how much time they will meet. If you consider the actual path followed, this is the actual path followed. And if you have to find the time, you'll have to take what is the velocity at the different instant, and in that case, for how much time it has taken there to move through that. So that will be done only if you are using calculus, and that will be the use of the reverse calculus there. But as it is given in the problem that it is an equilateral triangle, all particles are moving towards one another with the same speed. So obviously they will meet at a point which is the centroid. So here, if you consider now that they will be meeting at the centroid, this is your A, B, C. So they will meet at the centroid. This is suppose the G, and this is your A. So they will meet at this particular point. Similarly, this one will also come here. This is like this. So now if you consider here, you know that first, what is this length? AM will be how much? This is your D. This angle is 60 degree, equilateral triangle. So how much will be this AM? AM by AB will be equal to sine 60 degree. So AM will be your AB sine 60 degree, and that is your D root over 3 by 3. So this is the length A. Now this centroid divides the median in a ratio 2:1. So how much will be this AG? This is your 2/3 of AM. So it is 2/3 of D root 3 by 2, and that is your D by 3. So this is basically the distance AG. That is the distance they all will move. And now if you have to find the time taken to move from A to G, this will be equals to AG divided by velocity along this direction. It was basically moving in this direction initially. So this particular angle is how much? 30 degree. So it is the velocity along AG. And what was this AG? AG we have taken, it is your D by root 3. And this will be your V cos 30 degree. So this is your D by V. Of course, it is your root 3 here, and for cos 30 degree, root over 3 by 2. So it is 2D by 3V. This is the time taken. 2D by 3V. This is the time taken by the particle to reach at the point G. So this is what you have to find. After how much time they will meet each other. But now you may say that where we have used the relative velocity. We have not used relative velocity. We have just taken the component of the velocity in the different direction. We have taken how much distance has to be traveled. And accordingly, we have calculated what is the time taken. So let's try the same problem by relative velocity concept. For this, let's take the triangle again. This is your triangle ABC. A is moving in this direction. B is moving in this direction. Obviously, C in this direction. This angle is 60 degree. This is the direction at t equals to 0. So the component of velocity of B along BA, I can resolve this one in two directions, one perpendicular to this, other along this direction. So this component will be how much? V cos 60 degree. A is moving in this direction, B will be in this direction. So this will be equals to your V cos 60 degree. Because in perpendicular direction also we'll have a component. And that component will be your V sin 60 degree. But I need only the component of the velocity of B along BA. So this is the component which is equals to V into cos 60 is half. Now if you take the relative velocity of A with respect to B along BA, this direction, or along AB, whatever you call. It is the velocity of A, which is V, minus velocity of B towards A. So this is your minus V by 2. Because the two are in opposite direction, V is in the A is moving in this direction, B is moving in the opposite direction to that. So in that case, it is equal to 3V by 2. What was the initial separation between A and B? That is D. When they will meet at the point, one point, when they will meet at one particular point, in that case, this separation will be 0. So relative separation to be covered, that is equals to D, till they meet at one point. So therefore, the time taken will be equals to D by 3B by 2, and that is your 2D by 3B. So this is how you can get the same expression for time taken by relative velocity. By this method of relative velocity, you can solve this problem easily. In continuation with this type of problem, let's consider now that we have 4 particles located at the corners of a square of side A, of side D. So again, here you have A, B, C, D, side is D, and again they are moving with the same speed. It is asked after how much time they will meet at one point. So they are moving with this speed. So same way we can attempt, and we know that they will be meeting at one point, that is the point of intersection of the diagonals. So in that case, now this AC will be equals to D root 2 or AO, that is this length, which is half of AC. So it is your half of D root 2, that is D by 2. And now if you take the component of the velocity in this direction, this angle is 45. So it will be your V cos 45 degree. So velocity along AO, this is V cos 45, that is V into 1 by 2. Therefore, time taken, that will be equals to D by root 2 divided by V by 2, or that is simply D by V. So this is the time taken. If you try it by relative velocity concept, here again we have taken in the same way. We have the square. This is your A, B, C, D. It is V there, side is D. Now if I take the component of the velocity of B along BA, so component of velocity of B along BA, that will be your V cos 90, because this angle is 90 there. So in this particular case, this will be 0. So now if I take relative velocity of A with respect to B along BA, this will be equals to B minus 0, or that is V only. That will be equals to V minus 0, that is V only. Therefore, the time taken, this is your D by V, which is the same expression we have got. So you can use relative velocity method for solving this type of problem. See, geometrically, you can solve this type of problem by this method also, and you are getting the same expression. But once the problem will be complex, in that case, you'll find that it will be easier if you try it by relative velocity concept. If it is just given that it is your hexagon, that the particles are there which are located at the corners of the hexagon, what is the time taken if they all move with the same speed towards one another? So that also you can try this by this geometrical method or by relative velocity method. Here it will be relatively easier. But in fact, you will realize its importance when it is said that we have a regular polygon of side n, and we have n particles located at the corners of that regular polygon. They all start moving with the same speed towards one another. What is the time taken when they all will meet at one point? So there, geometrically, if you have to represent, it will be difficult to represent a regular polygon of n side because n is not mentioned there. But if you try it by this relative velocity concept, you have to simply take what is the angle between two components there or two sides there. You find what is the velocity component in that particular direction and then find relative velocity. Once you have got the relative velocity, you can find time taken. That will be equal to the side length divided by relative velocity in that direction. So you can easily solve such type of problems. So these are the problems which we can do from the concept of the relative velocity.